Chapter 10, Problem 23. A 392 Newton wheel comes off a moving truck and rolls without slipping along a highway. At the bottom of a hill, it is rotating at 25 radians per second. The radius of the wheel is 0.6 meters, and its moment of inertia about its rotation axis is 0.8 mass times radius squared. Friction does work on the wheel as it rolls up the hill to a stop, a height h above the bottom of the hill. This work has absolute value 2600 joules. Calculate h. So we can use conservation of energy to do kinetic energy plus potential energy plus work or friction, which is equal to kinetic energy plus potential energy, initial. So our mass is equal to 392 over 9.81 over gravity, which is 40 kilograms. So we have that our kinetic energy, so our potential energy to begin with is 0, and so we just have that our kinetic energy is equal to our kinetic energy and our potential energy, which is 1/2 inertia times angular velocity plus 1/2 mass times velocity squared. So we can plug in our numbers for our inertia, which is 0.8 times mass r squared, and so we end up with 0.9 mass r squared angular velocity squared. So again, our friction is 2600 joules, but in this case it's minus 2600 joules because it's going up the hill and it's going against the tire, so it's negative. So we get that our kinetic energy at the end is 0, our potential energy at the beginning is 0, and our potential energy at the end is mass times gravity times height. So we again have this equation, and we're able to plug in some numbers again here. So our kinetic energy is equal to 0.9 mass times radius squared times angular velocity squared, plus our friction, which is equal to the potential energy here, U2. So when we have this equation, we're able to set it equal to h. And when we set it equal to h, we're able to plug in all the numbers that we have for mass, for radius, for mass, for radius, for angular velocity, for friction, and for gravity. And when we do that, we get that h is equal to 14 meters.